Okay, let's get started. Had another longish break between classes. So last time, I think we finished with the 180-degree hybrid. We looked at how it can be used to excite differential components. Specifically, we looked at LC resonator. And we tried to understand the differences between when the LC resonator is directly driven from port versus using the rat race, which included two main points. One, that the rat race coupler itself has a finite physical length, so it introduces a phase delay, so one has to take that into account. And the fact that the impedance seen by the resonator is now no longer 50 ohms. It was 100 ohms because it was 250 ohm transmission lines driving it differentially, which effectively gave you 50 or 100 ohms in terms of what the line width of the resonator is going to be. So in the second half of today's double lecture, we'll be looking at these resonators in a little bit more detail. We have covered them in various short forms throughout the lecture series so far, but we will look at a few different types of those resonators in detail. But we'll finish off these 4-port devices with a discussion on directional couplers using coupled lines. And again, I have mentioned this many times in the past, but we'll just look at it in a little bit more detail. The analysis again involves even odd mode analysis here, because you have two modes present here, and we will only look at the basic idea here, and you can read through the more detailed discussion. And then we will try to look at this in microwave office and see how this device functions, what exactly the different terms mean when we talk about the properties, the scattering matrix of a directional coupler, and then finish up with looking at some discussion using how to make this using different types of transmission lines. Okay. So the main point here is that whenever you have two unshielded transmission lines, okay, what they mean by unshielded is that the fields of one transmission line has to interact with the fields of the other transmission line. So if you remember the coaxial cables, which I had shown you earlier several times, the ones which we use to connect different components, they have a ground, but the ground also acts like a shield. So outside of the ground covering, ideally there are no fields existing, right? At the edges you might have some, but otherwise in the bulk part of the thing, there is no field outside the transmission line. So if I bring in two conventional coaxial cables and put them next to each other, they should not really be interacting with each other. There will be no interaction. So that's what it means by unshielded, which means that it will be either like a broken coaxial cable, or if you're using things like microstrip and strip line, there you can bring two of them close to each other, and you want the interactions of the electromagnetic fields to happen. And these generic structures are called coupled transmission lines. And what it means is that if you now set an excitation on one of them, it's going to induce something on the other and will lead to waves propagating on the other as well, and vice versa. And which means that power which is being sent on one transmission line will eventually go into both transmission lines, depending on exactly how the things are coupled. One has to worry about whether the TEM mode type of propagation, which is what we have assumed for all of our coaxial lines and strip lines, and we had commented that microstrip is actually only quasi-TEM. because of the lack of symmetry on one side. So strip line, remember, is a center conductor with dielectric on both sides and ground planes on both sides. Microstrip is only one half of that. So the top part is air usually, and the bottom part is dielectric, and that gives rise to the thing being non-TEM, and that has a consequence when you look at coupled line structures. So here is an example of what a coupled transmission line could look like. Now, this could be representing either a microstrip or a strip line, because there's not enough detail in this particular figure. But the thing you want to think about is that each of the transmission line, as it used to before, has some kind of a capacitance, to ground. This is the capacitance per unit length we talk about. So it's with respect to the ground of the transmission line. And if they are identical, then these two are going to be the same. But in addition, now you can talk about some kind of interline capacitance as well. Okay. So this can be a very simplified model or an equivalent capacitance network for thinking about the two transmission lines. Okay. So you can, if you now take these two transmission lines infinitely far apart, then they are two independent transmission lines, and you can think of them as two modes, right? There is one mode here and there's one mode here. They have nothing to do with each other, but the total number of modes is two. When you bring them closer, and as they start interacting, it will still have to be described by two modes, but those two modes are no longer going to be the same two modes as before, which were independent. Okay, so this is very similar to how we think about coupled oscillators as well. When the oscillators are separate, uncoupled, then there's a one mode here, one mode here. But when you bring them into interaction, then you get two new modes. So again, you can really think of them as some kind of normal modes of the system. And those normal modes will have some particular symmetry, but the whole thing can be described either in terms of the original individual modes or in terms of the new normal modes. It just gives you an advantage sometimes when you're analyzing the system. So here also, you end up with having the same kind of two modes, which that, earlier you would say that, okay, there is some voltage V1 and some voltage V2 with respect to ground. But you can now talk about things like V1 plus V2 and V1 minus V2, right, in general. And that, again, if you go back to our previous discussions on this even odd mode analysis, this sort of is like the even mode system, and this is like the odd mode system. So this way of thinking about it here, like thinking about this intercapacitance, allows us to figure out what we mean by those modes when we try to calculate. So for example, if these two transmission lines were far away and they had some characteristic impedance, when you bring them close to each other, then does it mean to talk about a characteristic impedance of the individual lines? Should I think about them as characteristic impedance of the even mode or the odd mode? That's basically what's going to happen. Of course, if you take them far away, they are individual lines, but when they're interacting, you can now start talking about properties of these even and odd modes, and they have a little bit more natural meaning because you can then separate these two modes because the two modes don't interact with each other, right? When we saw the, which was the circuit we analyzed using the even odd mode analysis? That was the, sorry, what was the first circuit we used? Oh, the Wilkinson divider, right? So there you saw this idea that if you excite the even mode, everything remains in the even mode. It will not transfer into the odd mode. In fact, that is the meaning of these when we call them normal modes, that they are non-interacting. So it allows you to calculate the properties of the things separately. But if you only excite, say, V1, then at some point it will get converted into V1 and V2, maybe with the prime because they're different now. So if you excite only one of the transmission lines, in generally you'll get both of them excited. But if you excite only the even mode, then only the even mode will be excited. If you only excite the odd mode, only the odd mode will be excited. Okay. So this is exactly the same as before. And now using the symmetry of these modes, you can start simplifying some aspects about this circuit, right? So the top part of this graph, so let me maybe zoom in here, is now talking about even mode where both have the same voltage on both the transmission line or the both parts of this coupled transmission line, which means that there is no current flowing across from one transmission line to the other transmission line because the voltage is always the same. So this capacitance here in between, which we had earlier drawn, this one, can effectively be removed, right? So you can now think of them as two independent transmission lines with this capacitor not playing any role. The fact that they are close to each other. Okay. And then, but this C11, sorry, in the case of the odd mode, where you now have V and minus V, you now have a point in the middle which will have zero voltage, right? So this is exactly what we had done, and that point will always be at 0 volts. And since in this picture the 0 volt is always connected with the ground, you can now take this capacitor, which was initially C12, you write that as two separate capacitors in series, and because capacitors add inversely in series, that's why you have these two C2 here, okay? And then you connect this to ground. Sorry?
This H volt and E volt.
Oh, that is just basically another way of saying the that there is no current flowing, so there's no magnetic field. So that's what they call by H wall. So H here is a magnetic field, and here the center point is at 0 potential. So there's no electric field over there. So 0. So that's what they are talking about here. Okay. Okay, so this is how this 2C12 and 2C12 comes on both sides. And now this again basically allows you to think of this, now this part is non-interacting. But if you now see the total capacitance with respect to this point to ground has two components, the original C11 and the extra 2C12 as well. So this already tells you that the even mode transmission line and the odd mode transmission lines have different capacitance per unit length, right? So that naturally translates to the fact that the two modes of transmission lines will have different characteristic impedances, right? That's basically the point of this analysis, to understand the equivalent circuit in the two different modes. This part is clear? So then you can go ahead and define these kind of quantities for the even mode and odd mode. So this is Z not E, okay? It's not, this is 0 and not O. And similarly, you can write one for the odd mode as well. But odd mode now has this extra capacitance here. So when you go from two individual transmission lines to a coupled transmission line, you now represent everything in terms of the even mode impedance and the odd mode impedance. The individual properties sort of don't make sense anymore once they are coupled. But of course, at the edges, if this is a finite section of a coupled transmission line, at the edges, you have to talk about what is the characteristic impedance of the system you're working in. So we will see later on when we look at the device, and that is always going to be a 50 ohm system. Okay. So that's the essential basic sort of picture of how a coupled line through interaction gives rise to even and odd mode. And then from there, you have two different impedances. Now, the question of whether this quantity here, this is the phase velocity, this is the speed of propagation of the waves on that transmission line. They have written here both of them as the same, right? Omega p here. And this is basically what determines, or this is connected to the fact of whether this can be modeled as a TEM transmission line or not. In the simplest case, the ones we'll be looking at, we assume that's true, which means that an even mode excitation and odd mode excitation travel at the same speed through this coupled transmission line medium. Right? Because the one of the devices we are going to look at, which is this directional coupler, it needs those two things to be the same. Otherwise, you can have some problem. Effectively, what it means is that the electrical lengths will be different for the same physical length. The electrical lengths will be different. And if you are setting up some kind of special interference condition, then that will not be satisfied for both even and odd mode propagation. So in general, there is no simple analytical way of calculating the combined characteristic impedance. You just have to either do some approximations or use a full finite element simulation to do this. So, these days, this is pretty straightforward. But in POSA, they give you this this kind of a chart, which is, of course, calculated numerically or through some quasi-analytical formula to help you design coupled transmission lines with different characteristic impedances. So it gives you the X and the Y axis here are the even and odd mode impedance you want. And then this tells you the dimensions, which is basically the width over the height. So S over B and W over B. So you can look at the model here. So let me zoom in. Okay, so this is for a coupled strip line. These are the ground planes, right? There is a dielectric of height B. So B is the total height. And then you have two transmission strips, like the central strips of width W, and the gap between them is S. So you introduce an additional parameter when you go from one transmission line to another, because the height is there, always there. The width of the line is always there. Now you have spacing between. And of course, we are assuming that both the widths are the same. That need not be true in general, but then the analysis becomes very complicated. And in most cases, you can of sort of practical importance, you use them as the same. Okay. So this chart basically allows you to pick those numbers. So basically what it means is that for a given B and a given scaled characteristic impedance, which is again connected to the dielectric constant also of the medium you're using, then you can go here. For example, this point means W by B is 0.4, S by B is 0.2, and that will give you an odd mode impedance of this value and an even mode impedance of that value. Okay, so this chart is there to guide, but we've been using these tools in the microwave office software in TX line. So we will see that in just a bit. We'll just put these numbers in there and we can get these directly. But otherwise, you can use these kind of charts earlier. And this, so yeah, this one is for strip line. And this one is for microstrip. Okay. But here they have mentioned that this is calculated specifically for a dielectric constant of 10, because unlike the strip line, which is the TEM, it doesn't, this calculation doesn't scale in the same way with just changing the characteristic impedance, because the phase velocities change are different, and then the calculation doesn't work. So let me say that again. Remember, there is this ER here, which means this table works for any strip line with any dielectric constant, whereas this table works only for epsilon equal to 10 dielectric constant. For every dielectric constant, you will have to recompute this particular fix for the microstrip. So this is the microstrip. There is no dielectric on the top. There's no ground plane on the top. So that's what they say here. For coupled microstrip, the results do not scale with dielectric constant. So design graphs must be made for specific values.
So if increasing is Z even is with increasing pace, Z even is increasing and Z odd is increasing. So how many years?
Increasing S, maybe let's look at the strip line one. So increasing S is in this direction. And you're saying that if I go from 0.2 to 0.1, the even mode impedance is coming down and the odd mode impedance is going up. Yeah. That's right. Yes. Yeah. So you're asking how to think about that? Let's do the reverse. If my two transmission lines are far away that they're not interacting, what would be the even and odd mode impedances? So each transmission line has a characteristic impedance of Z0, and they are not talking to each other, like they're far enough. But I can still define an even and odd mode, right? What would be the odd mode impedance in that case? Sorry? I think I need to buy you a microphone and a speaker. What should be the same? Z0 and?
Z0 for even and odd if they're far.
But same and equal to what? No. So we are saying the individual transmission lines have characteristic impedance Z0. So you're saying that odd mode impedance is Z0.
Whatever L is upon C, but there.
No, so you only know that the individual, see, when they are far away, they have an individual identity, right? It's a strip line with characteristic impedance Z0. This one is also a strip line with a characteristic impedance Z0. So if they are non-interacting, what is the even and odd mode impedance? You're saying it's same, but same in equal to what? Z0? So something multiplied by Z0?
Is far apart, then C12 will be less. And I think in that case, only impedance will be
Well, C12 will be less or 0. So if C12 is 0, then
there will be only C11 and C1.
so if we go back to this formula here, the odd mode impedance is anyway even mode impedance was anyway only related to C11 or C12. That has remained the same. So this even mode impedance is going to be the same as the whatever the impedance was, right? Because C11 and C22 are the individual capacitances per unit length. The odd mode impedance is related to C11 plus 2C12, but this is now 0, which means odd mode impedance is also C11 or C22. So which means even and odd mode impedances are the same and equal to Z0 itself. Okay. So now if you start bringing them closer and C12 now starts to grow up, what will happen to the odd mode impedance? Yeah. It will come down, right? So when the transmission lines start interacting, the odd mode capacitance per unit length goes up that means the impedance will come down for the odd mode. So that explains that with larger distance, the odd mode impedance is only going to go up and vice versa. The even mode is a little bit more tricky to understand because that is not obvious from the way we have analyzed this problem. Because it looks like the even mode impedance anyway only depends on C11. So whether it is far or closer shouldn't really make any difference to the transmission line impedance. Whereas this one says that if I go from say here to here, my even mode impedance also comes down. Yeah. Edge coupled is basically this diagram. This is what we have been looking at. So these are the edges, right? So, okay, why this terminology edge coupled? Because you can have, I think it's called broadside coupled, where you can have the lines going top, bottom. And remember in one of the previous lectures, I had shown two lines sort of crossing each other on either side of thin. So that is the difference between the two types. So here we are only talking about edge coupled only. I don't have a very convincing answer for why the even mode impedance comes down.
But width is also convenient.
Huh?
C11 itself is convenient.
No, width is not.
That's width down.
No, we are staying on constant width and yeah, because I'm on this line. So this line is W equals WB equals 0.2. We're just traveling along this contour, which is fixed width, but changing gap. And what he's saying is that as you come from 0.2 to 1, with increasing that's increasing separation, the odd mode, I keep getting the Z naught E is like really confusing me. The even mode impedance also.
It's like, so the height is also.
Really? Can I not keep the height fixed and still travel on S by B equal to change? So B is fixed, W is fixed. Only S is changing. I mean, at least that's the way to interpret this curve, right? You can choose this curve if you want. But this point here is at a higher value of even mode impedance than this point here.
Because I think that the two can change in the C1 and C2 to itself because of two strip line.
That is logical. That is the explanation I also have in my mind, but it doesn't follow from this because they have not talked about how C11 and C22 itself would change as you bring these things closer. So essentially, I think the general point is that both capacitances sort of go up as you bring this together. So impedances come down as you. The
change should be symmetric if any change happens.
And actually, no, sorry, but that's opposite of what is happening, right?
No.
Because if the capacitance goes up, it's sort of the other way around, because I guess because there's some extra capacitance going to the odd mode, the even mode capacitance is actually effectively decreasing. Sorry. Look, this direction is increasing gap. So we are talking about bringing them together, which is the opposite direction. And there the even mode impedance actually goes up as you bring them together. Okay. We can actually see this when we open up the model and see, but I think it's the opposite argument that when you bring them together, there's some capacitance now between these two. So the capacitance to ground itself goes down a little bit, and that causes the impedance to go up as you bring them closer. But eventually, the point is that if you start from close by and take them far away, they both should end at Z naught, right? And as you bring them closer, odd mode goes down and even mode goes up. And later on, you will see that for some section, they have to satisfy some overall property that Z naught, the odd mode, even mode, and the original characteristic impedance, they have to share a relationship. They cannot be completely arbitrarily different from each other.
Can we make even almost like even in V1 plus V2 example, or in V1 minus V2?
Yeah.
And why decreasing the gap or increasing that V1 minus V2 point, whatever it is in the norm, it is also decreasing the division. So it will have impact on the V1 plus V2 even more.
No. The V1 plus V2 and V minus V2 is just the symmetry of the excitation modes, right? They have no meaning, they don't change. I mean, the definition of even and odd mode will not change with the interaction. Sorry? See, the actual value of V1 and V2 is completely irrelevant. Remember, your scattering matrix, which tells you the functioning of the whatever network you are looking at, is all about ratios of voltages. So what voltage it is, it doesn't matter. We are not talking about that we are only putting V1 at one transmission line and then I'm bringing in another transmission line, then what the V1 and V2 will be. That, of course, will be different. But we are only talking about in a given situation, when we excite even mode, odd mode will not get excited and vice versa.
Is there like some scaling effect of other on?
That's another way of saying what I was saying, that somehow the overall capacitance needs to be
Charge distribution is taking place.
exactly. Yeah.
Fringing effects.
Not fringing effects. I mean, there is no all of these analysis is supposed to ignore or at least assume identical fringing on both sides. This is basically because of the interaction between the two transmission lines. Maybe this example might answer that question. Let's see. Okay, assume W is much greater than S. Okay, and W is much greater than B. So they say capacitance per unit length of broadside parallel lines with width V and capacitance and separation D. Oh, wait a second. What is D here? Oh yeah, this is just the strip capacitance with respect to ground. But now it says C11 is formed by the capacitance of one strip to the ground plane. Thus the capacitance per unit length is, why is this B minus S? Side. Oh, so this is broadside coupled, sorry. 7.26 B. They're talking about this one. Sorry, that's not the right example. So using these kind of systems, one of the most important device one can make is these directional couplers, or it's also called couple line couplers. And what you find is that just with a single section, which means a length of transmission line of the right length and the right choices of even and odd mode impedances, gives you a 4-port network. Because remember that you have these you have these two transmission lines, and each, so that means you have 4 ports, right, for a section. And we of course assume that our system is the standard 50 ohm system, so has some characteristic impedance Z naught equal to 50 ohms. And then you just have a section of this coupled transmission line. And by choosing the even and odd mode impedances in a particular way, you can get a situation where, provided everything is terminated with the matched loads, which is 50 ohms or Z naught, you have arbitrary coupling, input port matched, port 4 isolated, and port 2 is the, okay, I guess the numbering here is different. Let me write the numbers in the right way. So that's the input port 1. Port 4 is isolated, so that is this one, 4. And through port is 2, and the coupled port is 3. So what it means is that if I send in power at port 1, most of it will go to port 2. And this is something we have seen. Remember, we have seen the directional coupler before in our, when we are looking at the VNA demo. Nothing goes to port 4, and a certain small fraction comes to port 3, which is called the coupled port. So some of it is obvious, and I had mentioned this when we were looking at directional couplers. I mean, from port 1 to 2 is just a straight transmission line, right? That's just the original transmission line. So you still expect that most of the power from 1 to 2 is going to go through undisturbed. Now that automatically tells you the regime in which this device is going to work is that the coupling between these two lines cannot be very strong, because you don't want too much power transfer to happening from one transmission line to another transmission line. So this only works in this weak coupling, even though the analysis sort of doesn't specifically assume that. And the port which is isolated is actually this port 4, which is opposite and across. And the one which is right next to the input port is the coupled port. And of course, this is completely symmetric. So any port can be used as input, and then correspondingly, all the others will change accordingly. So if you choose port 4 as the input, then the 3 becomes the through line, 2 becomes the coupled line, and 1 becomes the isolated. If you start from 2, 1 becomes the coupled, 3 becomes the isolated, and 4 becomes the, 1 becomes the through, 3 the isolated, and 4 becomes the coupled port. Okay. So the this section then talks about, again, using the even odd mode analysis, taking this as a particular length, and then calculating the effective input impedances at the location. So this is now a particular example of how it might look like in reality. And you see this requirement, the actual device is only up till here, right? That's the coupled transmission line. You need some way to interface to it, right? And that can only be done if those transmission lines are sort of taken further away, because practically you need to put some connector. And here, if you notice the width, I mean, this of course is a cartoon, but still, if you see, this is the width here is not the same as the width here, because this width here is basically for 50 ohms, right? That is whatever matched port you are putting here. And in fact, I mean, this is sort of a side comment. In the actual design of this kind of a device, how you take this line away from itself can have a little bit of an effect, because, you know, it's only going to separate out with some finite distance. So how do you say that, okay, the coupling is, we are getting coupled transmission line up till here, and immediately after that it's zero coupling? So there's going to be some interaction here as well, but hopefully it is small. In a design picture seen later, you will see that you can actually also make it perpendicular like this as well. But this edge effect can have some impact on the performances. In the analysis, of course, we do not consider that at all. And I mean, there's no simple way of analyzing this, rather than maybe breaking this up into several sections and calling them coupled transmission lines with different coupling and then seeing how that maybe affects the overall performance. So often these kind of decisions have to be done with intuition, and then these days with electromagnetic simulations, you can just fine tune the geometry and see what gives you the best performance. So they analyze this using the even odd mode, and I will not go through that here. You can take a look at it. And what you arrive at are actually these important equations. A natural term comes in, which is used and identified later on as this coefficient, which we call the coupling coefficient C. And that's the difference between the even and odd mode impedance divided by the sum of the even odd mode impedance. And which later on, for the right length of the coupled transmission line, turns out to be the coefficient of the port number 3. So remember, port number 3 was the coupled port. It was 1, 2, 3, 4. So this is the coupled port. So it gives you the voltage ratio from port 1 to port 3. V0 was the original excitation on port 1. And V2, which is the through line, is basically 1 minus C square, because this C square is the power coupling coefficient, and that gives you the through part. So of course, it's not 100%. So whatever power comes out of C, that power has to be subtracted. But we assume that the C is a small number, usually something like 0.1 in voltage units. So it's 1% in power units. Okay. So the important, from the point of view of constructing the device, basically the formula is this. So if you want to construct a coupled transmission line based directional coupler with the coupling coefficient C, because that's the only relevant parameter, apart from saying that it's the matched device, then you need to choose the even and the odd mode impedances based on this formula, where Z0 is the system in which you're working. So for us, it's always 50 ohms. So here you automatically see that if C is a small number, but positive, it has to be positive, it's a coupling coefficient, then even mode impedance is always going to be greater than the characteristic impedance, and the odd mode impedance is always going to be less than. But if you multiply these two equations, you see that this C stuff cancels out, and you get that the product of even and odd mode impedance is Z square. Right? So you saw something similar in quarter wave transformers, where the transformer impedance square was related to the two impedances. Here you get something similar. And this also is what I was saying earlier when we were discussing this idea of what happens when you bring them close. They are not completely independent of each other. So only one cannot change without the other one getting affected. And it's mostly this, as you were saying, it's some redistribution of the fields which changes the effective capacitance. Right. And I think part of the confusion in thinking about that is that with this even odd mode analysis, we actually always are considering only one half of the mirror image picture, right? But the even mode involves both the transmission lines. They're doing the same thing, but they're not doing the same thing when they're far away. Sorry, that's sounding really strange. But as they come together, this mode's capacitance, the combined capacitance, starts to get affected because of the interstrip capacitance as well. So whatever C you choose, you always have to satisfy this, right? So if C was 0, which is basically what we were thinking about earlier, that they're far away from each other, so there is no coupling, then even and odd mode impedances both turn out to be the Z0, which is the same as 50 ohms. So this is actually, we haven't come across this, but it's something you might encounter while thinking about this even odd impedance, and also connected to our last lecture's discussion on the 180-degree hybrid, that the convention is such that the even and the odd mode impedances turn out to be the same. Because I remember when I was studying this for the first time, I got a little bit confused. There's a factor of 2 problem, which is, and I think I mentioned this in the last lecture also, is that you have we had this picture where we had this LC resonator. Driven in odd mode. And we said that it actually sees 100 ohms, right? This was 50 and this was 50. And we said that this system actually sees 100 ohms as a dissipation. Now you can think of this as the same way that, okay, this is odd mode excitation, and these are two individual transmission lines of 50 ohm each. Then according to this, it's supposed to be 50 ohms, right? The fact that I have not put any transmission lines here doesn't really matter, right? It's going to be a 50 ohm transmission line. But if they are now, these are non-interacting transmission lines. So it's the same as saying I have two independent transmission lines. But the effective dissipation this guy sees, which is sort of saying that what is, if I extend this out here and just say that what is the impedance sort of seen here, which is some, it looks like 100 ohms for the definition from the point of view of this guy, but from this thing it looks like 50 ohms. So which is the correct one? I think this is basically got to do with the convention. I think an extra factor of 2 comes in when you actually define the characteristic impedance, and that will automatically, change what the voltages here are going to be transformed to when you think about that. So this is just to keep in mind if. Because when I was doing this, I was analyzing these using even and odd mode, and I got factor of 2 wrong, and it took me a long time to trace this to a convention. Okay. So at the end of the day, the design principle is actually very easy. All you need to do is you have to decide C based on your application. And as I said, C is typically 0.1 or 0.01 in power. And then you just know the even and odd mode impedance you need to get in order to achieve that. The length is lambda by 4, so that I forgot to mention. So the length of this transmission line is lambda by 4. And that's it. So you need to essentially now compute what is the, so your B is given, right? And then you need to compute this W and S. Choose them such that you get the value of odd and even mode impedance you need, and then this whole thing should work for that. So let's take a look at this in using this example itself they have given, but I will move to the microwave office. So let me actually write this down here. So it says 20 dB coupler, which means power ratio is 0.01, which implies that C is 0.1. If you do the calculation, you get sorry. So the other things they have given is they have given things about epsilon R is 2.2, and the ground plane to ground plane, so it is B, is 0.32 centimeters. Given the film thickness is 0.002 inches. Did you see if Binoy was using the system? Oh, this you are using. Okay. But there's no simulation running, right? So this HFSS stuff you were running. But what simulation were you running then? What I mean is that is CPU being used? Okay. Okay. So let's first go to TX line. And go to coupled strip line. So here. Dielectric constant is 2.2. They've actually given a loss tangent for the dielectric material as well. So yes, don't know if that's possible to define here. I guess you can, yeah. Let me keep that for now. And B is, it's funny, all these numbers have changed before I typed it out. Height B is 3.2 centimeters, so that's 3200 microns, right? It's 0.32 centimeters, sorry, yeah. Dielectric constant is there. Center frequency they want to use is 5 gigahertz, so put the frequency here as 5. And now we start setting, and the thickness is 2 mil. For the, this is the strip thickness. Sorry? Oh, it's 3 gigahertz. Okay. Anyway, that should really not affect. It just changes the length of the transmission line one has to make. Okay. And now I can start specifying the width and the gap to get the so let's do this. And then so it says for this an even mode impedance of 53.62. Okay. Yeah. So this 2.59 and 0.98 numbers are actually what POSAR calculates. So in fact, I had noticed this when I was setting this up, is that the numbers they have gotten for the dimensions doesn't give the same even an odd mode impedance when I use that here. So I've used all the numbers from POSA, but we'll adjust that in just a little bit, because for this combination of width and gap, the impedance is coming out to be 53.62, whereas they had calculated that they want 55.28. Okay. And the odd mode impedance is coming out to be 43.66. And what we actually wanted was 45.23. Okay. So we'll adjust this, because initially I said, let me just try it with this, because there's also always a possibility that what TX line calculates and what I ultimately implement in microwave office might not also match. So the model we are going to use here is the pre-solved models. Remember, I had introduced these to you some time back. So in the elements, these are under strip line and coupled lines. Okay. So I've used the simplest symmetric edge coupled strip line model, which is already what I've drawn here. This is a pre-solved model which allows you to specify dimensions, so width, gap, and the length. And associated with all of these pre-solved model, there has to be a corresponding substrate definition. Okay, that substrate definition again comes here under substrates, and then this one I've used is S sub, which is the balanced strip line substrate definition. So that is what is here. Here you have entered the correct dielectric constant of 2.2, B of 3.2 millimeters. The loss tangent here was 0.05, okay, basically same. And rho is related to the film resistivity, and it's normalized to copper. That's just the definition how it is. So rho equals 1 means that I'm using copper as the thing. Now, the use of both the loss tangent, which is related to the dielectric loss, and finite resistivity means that we are now considering these transmission lines to be slightly lossy. Okay. So they will not have the most ideal performance, but it will be mostly the same. We can look at it by changing these to 0 afterwards to see if that improves the performance or what effect you actually get. One obvious effect, of course, will happen is that your through transmission will no longer be 99%. It will be 99% followed by whatever attenuation you get in that line. So usually if the lines are small and the loss is not very big, it's not a huge problem. Okay. The port definitions are unfortunately not the same as the one in the book or what we have done before, because it was 1 was here and 2 was there, and 3 was here and 4 was there. So maybe to keep the thing consistent with what we did. So see, that's the port numbering on the device, but the ports I have chosen matched it, but I can change that now. Let me disconnect this. And bring port 3 here. So that 3 becomes the coupled port and 2 becomes the through port. The port number 4 is the same. Okay. We go to project options, and oh, we forgot to set one thing, which is the length. Actually, I know why all those numbers changed, because I opened a new one. Yeah. So I have to adjust this physical length so that I get an electrical length of 90 degrees at 3 gigahertz. So currently it's at 3.4 millimeters, which is giving about 18 degrees. So I need to go roughly 5 times. So that's going to be like 18500. It's too much. It's close enough. So 17 millimeters. So I have to enter that here. 17. So let's go from 0.01 to about 6 gigahertz. And already defined a graph with all the transmission coefficients. S21, 31, 41, and 11. Okay. So let's look at this carefully. S21 is the through port, okay? And that's basically close to, that's the blue one, essentially close to 0 dB, right? Which is what you expect it to be. S31 is the coupled port. That's the one we want to be tuned by choosing this coupling parameter. And you have to look at the value at 3 gigahertz because that's the design frequency. And you see it's close to minus 20 dB. It's slightly higher. And this is probably because of our slight difference in what Posar gives and what this guy is calculating. S41 is the brown one. That's the isolation, which means the port where no power should go. And it's only about, so it says minus 30 dB. So it's about 10 dB less than the coupled power. So this is not so great, right? You would expect the isolated port to ideally have a much smaller value. And the last one here is, oh, sorry, wait a second. Did I look at the wrong one? No, I looked at the wrong one. So S41 is the brown one, sorry, right? See, look at the shape of the marker here. So that's this one here. So it's not too bad. It's about minus 50 dB. It's about 30 dB less power than the direction. So see, this is the intended direction and this is the unintended direction. So there's 3 orders of magnitude difference between. So it's decent. And S11 is this orange with this hourglass kind of marker. That's the matching part. Okay, so that's minus 30 dB. It's pretty decent. Okay. So, and then these numbers sort of start to deviate as you go away. And because that's the, the intended operation, but it sort of still works as a coupler because the matching and the isolation is still okay. It's just that the coupling value is now going to be smaller as you go away from these things. This is again purely because this is a lambda by 4 section. You design this special length for one frequency. So it will have all the standard properties. And again, designs which use multi-section, and there is a small discussion in Posar about multi-section transformers that uses many such lambda by 4 sections interacting with each other to increase the bandwidth of operation. So that will give this, how quickly this falls off can be improved. Okay, so let's try to see if we can tweak the numbers. So one advantage of this pre-solved model is that unlike the EM simulation, this is much faster. Okay, but it's still close to a physical model. It's not an ideal electrical model. It uses some formulas which have been pre-solved for a particular geometry, and then gives you a model here. Okay, so remember, we only 2 things we can control is the S and the W. So the width and the gap. The length has no meaning. The length will only, if the length was wrong, the frequency, the special frequency would be slightly off, right? So that's not so important for us right now. So let's play with the width here. So I'm decreasing the width and I'm looking at these parameters. So I don't see, actually, let's go back and let me freeze these traces so that we can look at this as a reference. Okay. So it's getting better. So remember the ones which are changing is the isolation and the port match. Okay. Both of them are going down. The other 2 are hardly changing. And that kind of makes sense because these things are like already several orders of magnitude below, right? And this is some fine tuning we are doing. In a real device, you will never get this kind of performance as well, because getting reflection at -50 is very difficult in practice. But since we are looking at some idealized models here, we can see what this model tells you. So it's now getting smaller and smaller. And here it's sort of very small. And if I go further, it comes back up. Okay. And these big jumps are meaningless, right? This is all in log plot. You're talking about 6 orders of magnitude versus 7 orders of magnitude. Doesn't really make a difference. Okay. So that seems to be the ideal value of W. Let me see if I tune the S, if that also gives me, no, it looks like that is the ideal value. So this has now become 2.46 and 0.98 for the width. So let me go back to TX line and plug in these values. So width is now 2.46. The gap is the same. And now if we compare this, the odd mode impedance is coming out to be 44.95 as compared to 45.23, which is what we had needed. So it's closer, right? It's closer to what we had. And this one is now, even mode is 55.56 compared to 55.28, which was calculated from Pozar. So, and if I now go to 3 gigahertz and look at the coupling factor, it's still about the same. Doesn't seem to make a huge difference. So the slight mismatch between whatever software they use to calculate and what's being used here is one of the reasons for this thing. So otherwise, basically it's saying that port matching and this thing is as good as it gets. Okay. Let's just look at this in, instead of in log units, let's look at this in regular units. So now see the through one, it's about 0.99. The coupling is 0.1 as remember the V2 over V0 was square root of 1 minus C squared. So, and this is 0.1 as designed, slightly larger. And these are effectively 0, which is what we wanted. It sort of works over a reasonable range of frequencies around the design frequency. So I'm kind of surprised that even with these losses put in, it has given me this kind of a solution. Oh, but the tan delta somehow became 0. How did that happen? Yeah, I think I must have accidentally made it 0 earlier. So now you see that there's an effect of loss showing up in this curve, right? As the frequency increases, so loss tangent, when you define it, usually means that the loss increases with frequency. Hey, there is no asset, it's online. Yeah. Okay. All right, maybe that is actually more confusing than, so we just keep this 0 for now. Maybe even keep this 0. I hope it doesn't complain. No, it's okay. Go back to dB units. So one one derived quantity related to this directional coupler is something called directivity. Okay. So in port 1, port 2, port 3, port 4. So remember that the number which we specified was the coupling factor. And then we worry about the isolation, which is 1 to 4, right? This is called isolation. The larger it is, the better system. But a combination of isolation and coupling factor is a quantity called directivity. Okay. What does that mean? It's basically, if you remember, I had told you that the directional coupler, it's also called directional coupler because of the preference in the where it couples the power. But we talked about using it for doing reflection measurements, right, to separate waves propagating in two directions. And the way we had done it is by putting some device at the end of this port 2, right? That's one way of doing it. Is if you now send in, wait a second, no, that's the opposite convention. Just give me 1 minute to think about it, because we do it slightly differently than how it is done. Okay. Yeah, so let me just walk through this and maybe I'll remember. So if I send in power at port 2, that signal will mostly go towards 2, but 1% will be coupled to port 3. Yeah. And I can use by putting a measurement on port 3, like putting a power meter or a sensor, I can determine how much power I'm actually sending into from port 1, right? So that is a measure of the incident power in the system. I'm just defining it right now. You'll see why it would be incident power. That power goes to port 2, and then there is some device there whose reflection coefficient you're trying to measure. So that signal will bounce off and come back through port 2. And then that power which is now coming into port 2 is going to be coupled 1% into port 4. So port 4 can also become now a measure of the reflected power, right? At the same time, instead of port 4, you could also just measure the power which is coming back into port 1. But let's say we don't have access to both points there. The point here is that the incident power going from port 1 can be sampled at port 3. And the reflected power coming at port 2 can be sampled at port 4. So you have two independent ports to measure the incident power and the reflected power. And then once you do that, you can compute the S parameters, right? The reflection coefficient. Now, this would be fine as long as the isolation is 0. I mean, the isolation is perfect, right? Because otherwise, what's going to happen is part of the power which you send to port 1 is also going to end up at port 4. And that is going to interfere with the reflected signal you have sampled. And the same thing on the other side, that the reflected power which is coming from port 2 and should only have gone to port 4 will interfere with your incident power sampling at port 1 because it will come out of port 3. So this difference between coupling and directivity, and isolation, gives you a number called directivity, which basically tells you how good this directional coupler is at separating the two kinds of waves, the incident wave and the, because that, remember that if isolation was only 40 dB and coupling was 20 dB, the concerned signal you are trying to measure, the signal you are trying to measure is 1/100th of the actual signal, and the interfering signal is 1/10,000th of the signal you are trying to measure. So that's okay, because that's like 1% interference on the thing. But that's why it's coupling minus isolation, because the coupling is also reducing the amount of power you're actually measuring, right? Original power is 1. Wanted power is 0.01. And then there is some unwanted power. So you have to compare the unwanted power with the wanted power, which is already small compared to the original signals. So, and the reason that also makes sense is that because I can make the isolation larger by making the coupling also weaker. But that doesn't help, because then you are like even measuring the wanted signal also goes down. So that's why it's the difference between the coupling and the isolation. So coupling is 20 dB, isolation is 40 dB, then directivity is 20 dB, 20 and 40 ka difference. So it's that ratio you want to maximize to be able to get a good handle on this reflected quantities and incident quantities. And this becomes a very important component inside a vector network analyzer, which is what this kind of measurement does. And often they have multiple such, something called a dual directional coupler, which is sort of two of these directional couplers connected back to back. And in the last lecture, I will be discussing briefly about this, about this, a few scattered set of special topics, where I'll talk about this dual directional coupler as well. Okay. So before I stop for a break, let me quickly try this now in microstrip. Okay. We have done this in stripline where it works well. And maybe I will freeze this trace here as reference. Let me clear this. So I go for the same thing. I now go to microstrip coupled lines. And try to find the simple one that's here. Okay, and I also need to find the corresponding substrate for that. And that would be M sub. Let me just make sure it's actually M sub and not something else. Yeah. So this time we will find the parameters which match the impedances rather than the numbers. Anyway, we don't have any numbers for the microstrip from POSAR, but we'll use similar, go to coupled microstrip line, use the same dielectric constant as 2.2, set the loss tangent to 0. I will choose the height as the height was, what was the height earlier? It's 3.2 mm. So half of that, let me choose that. 1.6. I'm choosing half because strip line has both sides, right? Thickness is 2 mil. We're using something like 15,000 microns for this. Let's see. Copper. Wait. I'm just guessing now, just find the numbers. Okay. Gap is too small. Let's try 500. This needs to be bigger. Okay, even mode impedance is too high right now. Sorry, do I need to increase the width? 92. Oh. What is the odd mode impedance? Okay, that's in a reasonable place. So I need to lower that as well. Let's see. So we need 55. So you see the strip has to be much wider because there is dielectric only on one side. In fact, maybe to make things simpler, let's increase the dielectric constant so that these impedances are more, these dimensions are more reasonable. Otherwise, it will become very large. Okay, so even with dielectric constant of 6, I have just about reached 51 ohms. So, okay, 55.28 is what I needed, and I have 55.62. Okay, that's close enough. Odd mode is 30. So I need to increase this. 32. The dielectric constant is too high. So I remember when I was trying this with microstrip, this was one of the problems that even in the odd mode don't like to come too close to each other in the microstrip version. So what's happening to the even mode? Okay. -2. One. Wow, it's really strange. It's like, did I make a mistake somewhere? 1.6 mm, 2 mil thick, frequency 3 gigahertz. It's like the gap is bigger than the width. Doesn't seem to make any sense. I think I was just too far off from the correct sets of values. So now it's getting better. Even mode is 59. Odd mode is 47. So I need to reduce this. 45. 60. So 7. It's close enough. You can then tweak it. Anyway, remember that you can get any even and odd mode impedance, right? That formula tells you that if you choose a coupling constant and the characteristic impedance, that gives you an even and odd mode impedance. But if you choose any two even or odd mode impedances, that will give you some corresponding coupling and Z0 as well. So it will not be matched for 50 ohms, but that we can tweak a little bit as we go closer to better response. Okay, so let's start with this. So dielectric constant is 6. And so 2200, that's this one. So that's 2.2 and 1.5. This is all okay. I don't know what this thing is, but let's just set that. Oh, come on. Height is 1.6. The last thing is to check the electrical length. Now, this is where we will have a problem because you can see the electrical length for the odd mode is 106 degrees. And for the even mode is 118 degrees. Okay. So let's set the even mode to the right value. And see what happens. That's 11.5. And then the odd mode is basically a smaller electrical length because the speed is slower. Remember, the impedance is lower, so the speed is also slower. So length is 11.5. Just going to connect the same ports here. Right. Something got messed up. What happened? Oh. Right. Yeah, so if you ignore the last two, remember the scale here is really, really big. So it's not terrible. Let me clear the frozen and zoom in. So the through is still pretty good, right? I mean, that is expected that it will be the case. And the coupling factor is not minus 20 dB, it's close to minus 16. That's because we haven't gotten the impedances just right. And this is my isolation, which again is not so great. And the matching is okay, it's not too bad. So if I now tweak, but you also see that there is a difference in the response. If you remember, the strip line one had sort of a symmetric response. This one, some quantities are still rising. And this is really the consequence of the odd and even mode impedances, sorry, the phase velocity is not being same. So the interference condition is not meeting exactly at the same place. Okay, these are the wrong parameters. So first adjust the width. Yeah. You see, I'm not able to improve the directivity so much. Am I tuning the right thing? Yeah, I guess. Okay, so this has brought the coupling close to minus 20 dB. But you see this directivity is, the isolation is really poor, which means the directivity is going to be poor. So if you remember, that's what Posar was saying, that is very hard to do in microstrip. So I can improve the match, but I'm not able to make the isolation so much better. So you can try to play around with this at home to see if you can tweak it to be better. So we actually made one sort of device here. This is actually something my student had figured out to get it to improve performance. So it seems to have multiple sections in a different way. You see that it comes together several times and then goes further out. Okay, so let's pause here. Can I buy you all a cup of tea or coffee? I'm going to go get some and then we can come back. Or if you want to take a break from me, that's also okay. I can sit in a different table. So